the current slide. All right. Before we get going today, let me remind you of a couple of announcements. I know that most of you are probably already planning to go, but just in case you had forgotten, tomorrow morning at 10 o'clock on the Birmingham East Campus, the A.G. Gaston Auditorium, will be the presentation by, I think, UAB drama, thing. William Shakespeare's The Taming of the Shrew. Okay, I know that all of you are planning to go.
Oh yeah.
Yeah, it's a Shakespeare brilliant, and his plays are funny. This is a comedy, and it would be worth going to see if you have the time to do it. I'm afraid I'll be required to go. They haven't filled all the seats, so I'm hoping everybody will be there so I can do some work. But that aside, I've got...
So you keep telling us to go?
What's that?
You keep telling us to go so you don't have to?
That's about it, yeah. Okay. No, I'd like to see it, but I've got so much to do that I don't. It'd probably be better if I got my work done. But I've got to meet with the people from Copart and all that kind of stuff, so it's crazy. I may not be able to do it anyway. But anyway, it's a comedy. The twist on it that they're doing, Shakespeare's original work, he had the woman being very difficult, very opinionated, woman before her time probably, and the man's trying to tame the shrew, and it's very funny. Shakespeare has extremely comical situations there. Well, UAB's production, I don't know why or who came up with it, they've turned it around and having the man being very difficult, opinionated, and that kind of stuff, and the woman's trying to tame him. So that should be maybe just about as funny as Shakespeare's original, but we'll see. All right. And as far as my office hours go, I'm going to try to get down here to Pep Boys and get all my stuff out of the vehicle if they're still open tonight. I hope they're open till 9. If so, I can go by and get everything so that the thing's ready to turn over to them tomorrow. If they're closed and they have my key and I can't get in the vehicle, then I won't be on Birmingham campus the first thing. I'll be over here first thing. In fact, I'll probably be over here first thing anyway to make the exchange with them. And then I'll get back to Birmingham whenever I can. Or I'll stay up here and work here on this campus. So I don't know what my office hours will be like tomorrow. So if you're looking for me...
Would you like to know what time they close?
Yeah.
They close at 7.
7 tonight? Okay, well then I won't make it because you're going... What's that?
6:30.
Oh, no. Would I dare cheat you out of your tuition dollars? Not a penny. Yeah. No, but I wouldn't want to benefit myself at your expense. I would never do that.
I'll take you down there right now.
No, goodness gracious. That would just be terrible if I cheated y'all. Let it never happen. Okay. It's not that far. They said 8 minutes walking. I haven't timed it myself, but we'll see. I don't think that's right. All right. So I don't know what my office hours will be tomorrow. The odds are I'll be over here tomorrow morning. Whether I'll go back to Birmingham or not, I'll work that out with my boss and see. I may just work out here tomorrow. All right. Any questions on anything we've done up till now? Let's talk about what today's going to look like. We've got a slow start here, but we'll go until 5:15. We'll be continuing in chapter 2. Hopefully we'll get enough done to be able to do the lab at 5:15. I think we will. Okay? Then the lab will go 5:15 to 7:15, and then at 7:15 or whenever you finish the lab, you can start the test, okay? The test shouldn't take you more than half an hour. What's that? It's actually 10 questions, but most of them are multi-part. So there's like a total of 18 parts, that I'll be grading, A, B, and C on some of them. Okay. So there will be
every last little second.
I'm sorry?
Using every last little second.
Absolutely. Well, no, if y'all finish the lab early, you can start the test. When you finish the test, sayonara. You can take off. Doubt if you'll be done by 7 though, so I don't think I'll get the Pet Boys tonight. Okay, next issue. It seems like there's something else I was going to say on that, but we'll go from there. Oh yeah, I wanted to say this. I said it before and I want to make sure everybody understood. You can have with you on every test, including the final exam, Melba's here. Okay? And Kedrick's here. Anyone else come in since I called roll? Okay? Every test you can have a formula and equation sheet. Anything you want to write down on a piece of paper, front and back, as small as you want to write it, you can have every test. You can have a formula and equation sheet. Doesn't have to be formulas and equations, anything you want to write on the piece of paper. So if you haven't gotten that ready for the test, you could be doing that while you're listening to me, if you wish. And if you have some time between labs, you know, that kind of stuff. I'm sorry? I'm sorry? What's that?
Yeah, like your like the slideshow. If I can print it small enough and still read it, be on one piece of paper.
On one piece of paper, if you want to do that, you certainly can.
Oh, I'm asking.
All right.
Can I like take pictures of it? Off of the slideshow?
Use the one piece of paper?
On a piece of paper.
Yeah.
Got it on piece of paper.
Yeah. Keep it reasonable. I'll put it. All right. All right. Any other questions? Okay. All right. Here is where we begin today. If there are no questions on what we've done so far, let's hit falling objects. Now, before this, we were talking about horizontal motion in one dimension. Okay? Going straight line motion horizontally, and we talked about those features. Now we're going to talk about falling objects. Anyone know what this is?
Ball falling from top.
Okay. It could be. It could also be a ball being thrown from the bottom that happens to go right up to the top. The pictures would look identical. Okay, believe it or not, they would be identical. If you could time it so it should reach just there. But this is probably one dropped from the top. Okay? Now, this is one ball. It's not 7 or 8 balls there. That's one ball. And it's a time, what they've done is perfectly black room. Everything's total darkness. And they have a camera with the aperture open, wide open, total darkness. And then they have a strobe light. And it strikes every 10th of a second. That's what they took this, okay? And this is a strobe photograph of this ball as it's falling. That's 1, 2, 3, 4, 5, 6, however many shots of that ball as it did. So it's a strobe that's coming on and lighting the ball at different times. One aperture open, but it's capturing it on film that many times, okay? What do you notice about this? Observations.
It gets farther apart.
Further apart as it falls. Why would you think that would be the case?
It gets faster.
It's what?
It falls faster.
I can't hear.
It falls faster.
Why?
Because it's gaining acceleration. It's
Because what?
constantly gaining acceleration.
Yes, well, actually, the acceleration is constant. It's gaining velocity. Yeah, but I knew what you were meaning, okay? Therefore, the distance is getting longer. It's not a constant velocity, but it is uniform acceleration. The acceleration due to gravity, okay? And that's exactly right. Velocity is increasing, but at a uniform rate, so it's a constant acceleration, so the distances are also increasing. Okay, good observations. Here is the formula that is describing this motion. Now, this formula is assuming two major things, and both of them are reasonable assumptions. The first is that this is your 0 point, that is falling from the 0 point. Otherwise, you would have a D0 here if you were indicating this was coming from somewhere else. So this is your 0 there. Okay? The second assumption here, and it's reasonable, especially since the balls are close here, is that the initial position is 0. That's the first one. Also, the initial velocity is 0. If you threw the ball from here, then it would probably have a larger velocity to begin with, but once it left your hand, then it's still going to accelerate downward from that initial velocity, accelerating at the acceleration due to gravity. And we'll get to that in a minute too. So this is, since you don't have a V naught in here, in other words, initial velocity, or V sub I, and you don't have a D sub I, that means you're assuming both of those are 0. In the general case, you would have additional terms here. In fact, I'll write those out for you. If you had an initial velocity, you would be adding a VIT, and if you had an initial displacement, that would be plus DI. Okay, D meaning displacement, V meaning velocity. Your acceleration, by the way, falling, since we're assuming this is on the surface of the Earth, that would be the acceleration due to gravity. Yes?
So the plus VI is for initial velocity.
Initial velocity.
And D is initial distance.
Yes.
Okay.
If it started anywhere other than 0. Now, the kind of weird thing here...
That would be in addition to the R squared. So that anything you squared is already there.
Yeah, that 1/2 AT squared is the distance that's happening because of the acceleration due to gravity. Okay? This is a displacement. That's an acceleration. This is velocity. Think about the units here. Displacement, or let's say in meters or centimeters or inches or yards or furlongs or whatever. Okay? Velocity would be in meters per second, inches per second, millimeters per second, whatever it happened to be, furlong per fortnight, whatever that would be, and this D would also be initial displacement in meters or centimeters or whatever. So, since this is meters per second, you have to multiply by second. Since accelerations are meters per second squared, you have to multiply by time squared to get a distance. So units are your friend. Pay attention to them. Here's another thing to notice. We'll see this in several other formulas. There'll be one where it doesn't hold case, but all the rest of them is. Most of the time when the variable is squared, there's a preceding 1/10. Okay? Now, the reason for that comes out of calculus. So we're not going into that reason. Okay? The kind of the explanation they give in the book at some point, it'll be coming up soon, is that you're sort of using an average velocity, which remember was V initial plus V final divided by 2. So they sort of suggest that's where the 2 comes from. And if you want to think that, you can, okay? It actually is coming out of calculus, so you don't need to know where that. But you'll see that repeatedly. When the variable is squared, most of the time you have a 2 in the denominator in front of it. But like I said, there'll be one exception to that we see, but all the rest of the formulas with things squared, you will find that 1/2 most of the time in front. Okay. Now, the guy who came up with this, if you notice the picture at the bottom of page 35, the right-hand column of 35, according to the widespread story or the legend or whatever you want to call it, Galileo dropped 2 objects of different weights from the Leaning Tower of Pisa in his hometown of Pisa, Italy. That's not the P-I-Z-Z-A, it's P-I-S-A, Pisa. Reportedly hit the ground about the same time, discrediting Aristotle's view that the speed traveled during the fall is proportional to weight. Remember, that's what Aristotle said. He used now actually, one of the first times I taught either this course or the physics course before it, actually it was the physics course before it because that course didn't have a lab, so I tried to do demonstrations every now and then. What we did, I got someone to let me into a stairwell down in 259, that's the room I used to teach from, and went up as high as I could on the third floor, not on the roof, but third floor. Held out of a window and dropped a 1 kilogram mass and a 1 gram mass. 1,000 grams, 1 gram. From the third floor, as high as I could reach, dropped them at the same time. The students were down on the ground, and it hit 3 on the head. No, it hit the ground at the same time. Except it didn't the first time. I didn't know there was someone had strung a nylon thing, I don't know, it looked like fishing line or something like that, across there, and wouldn't you know, one of them hooked on it and stopped. But they got to that point at the same time. I did it again. They hit the ground at the same time. 1,000 times the weight, 1,000 times the mass, and they hit it at the same time. Now, it wasn't all that high, but still, Aristotle said heavier objects fall faster than light objects. No, Galileo disproved that. Okay. The following bodies, there's a little concept supplied, gives you 3 different possibilities to do. We did number 3 in class. I did number 3 in class last time or time before. And so anyway, you could do all 4 of those and get the see how that works. I wish I still had that crumble thing. It said drop it and the book at the same time, and they will fall at the same rate. Okay. Okay. So, we call this concept free fall. Falling objects and free fall. Now, supposedly what that means, falling under the influence of gravity without air resistance. Any place you're going to have no air resistance? Not on the surface of the Earth. In outer space, on the moon, Mercury, yes.
They did it in a vacuum chamber.
Yes, and you can do it in a vacuum chamber.
Did you see that video? Bowling ball
and a feather.
A feather or something, yeah, and they hit it at the exact same time.
Exactly. On one of the Apollo missions, when they were actually on the surface of the Earth, there's a picture of the astronaut holding a hammer in one hand and a feather in the other, dropping them, they hit the ground at the same time. Because there is no air to speak of on the moon. So, yes, we don't live in environments like that, though. Not for very long. Okay. So, the distance is proportional to the time squared. Okay? Distance proportional to time squared. The constant of proportionality, 1/2 A. And what is that A? Acceleration, and that happens to be the acceleration due to gravity. So distance is proportional to time squared. The speed increases linearly with time. That's a direct proportionality. This is directly proportional to the square of time for the distance. Now, the trajectories exhibit up and down symmetries. That's what I was trying to describe before. If you were to drop a ball from here, now what does drop mean? What's implied with the term drop?
Let go.
Okay, meaning?
You don't add any force to it?
Don't add any velocity to it. Initial velocity is 0. That's what it means to drop. So initial velocity is 0. Now, that would be exactly the same picture as if you threw the ball from below at just the right speed so it came to a stop right at your hand. If you could do that, that would be exactly the same picture. That's what it means. Trajectories exhibit up and down symmetries. So actually, to say that better, if you threw the ball from the ground upward, taking pictures as it went, at some point it will stop, and then it'll fall back down, and those pictures will be basically the same coming. The one going up and the one coming down, they would be just about the same. Okay? The acceleration is the same for all objects, because the acceleration is the acceleration due to gravity. And generally, that's a constant. Anywhere on the surface of the Earth, from the depths of the Dead Sea, the Dead Sea Valley, which is the lowest point on the surface of the Earth, to the top of Mount Everest, there's hardly any measurable difference between the acceleration due to gravity. So we count it as a constant. Okay? That's why, we'll get to this later, we can count weight and mass as proportional. They're not the same thing, but proportional because they only depend on the acceleration due to gravity. However, if you would go up into outer space, where you're far from the gravitational field of the Earth, then it's a different acceleration, if any. Okay? If you were on the moon's gravitational attraction is about 1/6 that of the Earth. So it would be a different acceleration due to gravity there. If you were on Mercury, you'd be burnt to a crisp. But it would have a different acceleration due to gravity. Venus, you'd be dead before you got there because it's a toxic environment. But if you were any other place, your acceleration due to gravity is different. So there, weight and mass are not equivalent. Okay? But on the surface of the Earth, they are. We'll get to that later. All right. So here's the deal. You drop an object, looks like a block here, from the top of this building. Okay? Now, if you're measuring the distance at which it falls, you use this formula. Notice I said if you drop, which means initial velocity is 0, so you don't need the VI term in there, VIT term, and we're going to count that as being distance equals 0 up there, so you don't need a VI term. So if you dropped it 1 second later, it's going to be 4.9 meters below you. Why is that? Okay? Right here, they sort of sneak it in here. The acceleration due to gravity in the SI system, System International, that's the metric, is 9.8 meters per second squared. Get used to that. 9.8 meters per second squared. So 1/2 of 9.8 is 4.9. So that's why in 1 second, when you square 1, you get 1. Okay? It will have dropped 4.9 meters.
What is, I can't see that. Where's the equation become?
Second,
That equation, what does that say?
D is equal to 1/2 AT squared. It's the same one we saw
Okay.
here.
What did you say,
Yeah.
as far as to remember, 9.8?
That's what I need to
Squared.
know.
Okay, what about
The 9.8 meters squared, what is that?
that's the acceleration due to gravity in the SI system, System International, the metric system, 9.8 meters per second squared. In fact, in a little bit, we'll no longer call that A, we'll call it G. That's classic, what they call the acceleration due to gravity. Okay? Now, and half of that, 1/2 of that would be 4.9. 2 seconds later, it's that same 1/2 of G, 4.9, but now you multiply it by 2 squared, which would be 4, and 4 times 4.9 is 19.6. So in 1 more second, it's gone almost 4 times as far. Right? 4.9 here, almost 4 times as far. Okay? In fact, exactly 4 times as far. In the next second, 1/2 9.8, that is 4.9, times 3 squared, 9, that would be 44.1. So it has gone 9 times as far in that next second. So you see, the distance is proportional to the time squared, not to time. Okay? 4 seconds, is that 4.9, 1/2 of 9.8 times 16, 78.4 meters is how far it would drop in 4 seconds. So every time, just like that pool ball that we saw, every time, every second, it's going further. The distance is increasing. And the next car here is going to get crushed. Not easy. Okay. So while the distance is proportional to the time squared, the speed is linear with time. Okay? Speed increases. In 1 second, V final is AT. We're assuming initial velocity is 0, so there is no, you're not throwing it. So all you do is your acceleration times time. What is acceleration? Change of velocity per unit time times time. That would be velocity. Change of velocity. V final. If the initial is 0. So that's 9.8. In the metric system, SI system, 9.8 times 1 is 9.8, times 2 is 19.6, times 3 is 29.4, times 4 is 39.2. These are velocities. Okay? That means from a very tall building that will be going quite fast. All right. Now, we're going to assume this is a fairly small, aerodynamically shaped object. So we're minimizing air resistance. But, and we'll talk about this in a later section, you know that the faster something is falling, the more air resistance. Now I can remember as a little kid, I liked doing this. My dad yelled at me when I did, but I loved when we were in the car sticking my hand out the window. Okay? It just was so cool. And when we're going at a slow speed, you know, going at a fast speed almost, yeah, you can just tell it because the air resistance is so much more at a higher velocity. So after a while, you can't ignore air resistance forever, okay? At very low speeds, very short drops, yeah, you can most of the time ignore it. Unless you have a sheet of paper, yeah, you can't ignore it with that. Okay. So that 9.8 is constant all over the surface of the Earth and for quite a range in the atmosphere and below. So we call this uniform motion, constant acceleration. Uniform motion. Okay? Or uniform acceleration. I'll say it that way. All right. So they kept the slide up there. Nothing here. I'm trying to see probably what would be there. Oh no. So let's look at back on page 36. I was wondering, I couldn't remember if they had it in the slideshow or not. They don't. But this is building up to this equation we've been using. This one here, d is equal 1/2 at squared. They do the steps that derive that equation. In reality, you really should be doing this with calculus. You haven't had calculus, you're not required to have calculus. So the way they do it, how they introduce that to there is from the average velocity being the average of initial and final. What is that true for? Uniform acceleration. Okay? And that's what they build it on, and that's how they derive the formula. Now, before we leave this on page 37, we talked about this before. I don't know if you've ever seen, well, and we talked about it. It's even in NASCAR racing or Formula whatever. What is that? Formula One racing or whatever. It's in bicycle racing. It's in running. It's in geese flying. Okay? The person in front encounters the most air resistance, and the people behind them, the air is disturbed enough that they can drag on the people in front. And that's what these racers are doing in the picture on the text. That's what runners do. That's what, now, the one exception to this is, y'all are old enough to remember this, but in horse racing it happens too. But I remember this one horse, y'all may have heard of him, Secretariat. Secretariat was just dadgum fast, okay? And the Kentucky Derby took off and left the field, won it, hands down. What's next? Preakness? I think so. Was the next race. A little bit longer, they said, not going to handle it. It took off, left the field, and said, Belmont Stakes, no way. This is significantly longer. It cannot sprint that far. And left the starting block, took off, left the field, and no one else came close. So if you're Secretariat, no one else gets close enough to you to do that. Yes?
Wasn't he just a few hundred yards away from the other horses when he was about to cross the finish line? Is that what kind of broke the record?
Yeah, exactly. Whereas usually there are a few microseconds ahead. That's why photo finishes. This had, like you said, 100 yards or something like this. That horse was fast. Okay. So it didn't work for Secretariat's opponents, but anyway. All right, there's a closer look at free fall at the top of page 38. It's a pretty good blurb to read. I think it's talking about some of the records that have been set in free fall, and there's some pretty amazing data there, okay? And I think they get into what they call terminal velocity there too. So let's move on. We've already done that slide, and that slide. Before we get into compound motion, I'm going to use this slide since it has some space on it. Not exactly white space, but close to it. Let's do the examples on 2.7. Oh, there's only one, 2.7. A rock that is dropped into a well, notice the verb there, dropped into the well. What does that communicate to you? Initial velocity is 0. If it wasn't, you would say it's thrown into the well. You gave it some initial velocity other than 0. Then you have an extra term there, okay? This one's dropped into a well. And hits, okay, here was the other thing I was going to say. This formula that we've been using, let's go back to it so you can see it. This is, and I've said this several times, but I may not have gotten my point across. This is taking downward as being positive. If you're counting 0 to be where you drop it from, downward is going to be positive because this is increasing. Your acceleration due to gravity is 9.8. P is a positive number. Squaring that, that's a positive number. These get bigger and bigger and bigger. That's assuming your 0 is at the top and you're increasing as you go down. So positive is downward. And a lot of times, physics and physics books and other things will always say up is positive, down is negative. And with that in mind, this book doesn't do this that much, but with that in mind, they say that the acceleration due to gravity is always negative. Because if up is positive, acceleration due to gravity is always toward the center of the Earth, which would make it negative. Now, this book doesn't do that, so if you go on to other physics courses, expect to see that negative 9.8 being the acceleration due to gravity. Okay. And that has bearing on this problem here too. The rock that is dropped into a well hits the water in 3.0 seconds. What's that a measure of? That's your time, 3.0 seconds. You could call it your delta t, the time interval, but we'll just leave it as time. Okay? Ignoring air resistance, how far is it to the water? So what are we looking for? Distance. Okay? Now, dropped into the well, initial velocity is 0, so we don't have to have an initial velocity term, and we'll assume 0 is at the top of the well, and how far it is to the water, that's increasing with distance, with time. So we'll use, what is your formula then? Second? 1/2 A t squared. And what's your A? Now, they didn't say what units you need to use. And so far, all they've said is 9.8 meters per second squared, acceleration due to gravity. In The U.S. customary system, we used to call it the English system or the British system. Now they don't even use it that much anymore. We're the only people who do, so they call it U.S. customary system. What is the acceleration due to gravity? Does anyone know? 32 feet per second squared. So 9.8 meters should be about the same as 32 feet. And it is. That's almost 10 meters, right? And a meter is a little more than 3 feet. So yeah, if it was exactly 3 feet, then it would be a little bit less than 30 meters, but it's not. It's a little bit more, so 32 feet per second squared. If you ever need it. They didn't specify here, so which do you want to use? In their solution they specified, but which do you want to use? Acceleration due to gravity. 9.8, the one we've been using? Okay, let's do it. 9.8, what units are 9.8? Units are your friends. Meters per second squared times, and it said it took 3 seconds, there's your time, 3.0 seconds squared. Okay, so that's 1/2 of 9.8 meters per second squared. Frankly, I would have gone on and taken half of that, but okay. What's 3 squared? 9.0, but you don't just square the number, you square the units as well. Second squared, even though I've never seen a square second. Never. Okay. Here, the units, the second squareds cancel out. One's in the numerator, one's in the denominator, so you can get rid of them. And 1/2 of 9.8 is 4.9 times 9. And this would be 81. It's 36 and 8 is 44. 44.1. What was left? Meters. That's not the answer they're going to give you. What answer do they give you? 44. Why do they do that? They don't always, but this time they did. You only have 2 significant digits here, 2 significant digits there. You can't get more significance out of a problem than you put in. So they dropped the 1.1. If that had been 0.6, they'd have rounded to 45. So it's a 0.1, so they dropped. So you'll see that in the text. Most of the time, I will not. Something else. Most of the time, I will not count off if you rounded incorrectly, but I will correct it for you. Unless, of course, it throws you way off in your final answer, then I'll probably have to take off something. Okay. Time out now. I meant to say this at the very beginning. I knew there was something I was forgetting. Several people, a few people, turned in the first lab last time. And every one of them left some of the questions blank. And I don't know, a lot of people, a few people turned it in earlier, and I had a chance to look at it first. I said, you left this blank. And generally what I got was, oh, I didn't know we were supposed to answer that. Oh, yeah. So let me pass these out to you. Now, if you don't want to change them, you don't have to change them. I can grade them on what you got. But I figured before I marked them all wrong, or blank, I would give you another chance. Don't want to do, but I'm going to give it back to you. Did we lose something altogether, or did we do it all? Okay. I think that was all the ones that were turned in. I started marking Rachel's, and then I saw. So let me say this, especially on these that are from the lab book. Okay, I should have said this before. I thought I did, but maybe I didn't. Anytime you see a big blank white space, that means they're expecting an answer. And if you read that problem, this is on page 16, number 6, describe a pattern or generalization concerning the volume of the cube and its surface area volume ratio. For example, as the cube increases, what happens to the surface there? Okay. They're expecting an answer there. So give me an answer. Okay. Now, things like 1, 2, 3, 4, 5, there's no big space there. It tells you what to do. Put it in the data table. That's what you do, okay? Or just it tells you steps to make. Same thing on page 17. All those are fairly close together. But on page 18, all of a sudden some white space. Guess what? Calculate the slope of your graph, okay? They mean write that slope in here. Calculate the experimental error. And that's why I was so surprised no one was asking me how to do an experimental error. I thought, wow, these people come in knowing all this stuff, okay? So you need to do that. If you have questions about it, ask me. I'll be glad to help with it. Number 10, number 11, both of those require you to write something down. Now, number 11, you'll see on all these, was the purpose of the lab accomplished? I know I mentioned that one because it says a yes or a no can be the first part of your answer, but it says why or why not. I don't want necessarily a dissertation on it. A sentence or two will be enough. And if you write down an answer, you get credit for it. Whether it's yes or no, or this was the lousiest lab I've ever seen in my life, it's totally worthless waste of time, you've answered the question, okay? I won't count off. That was your opinion, that's all it's asking for. All the rest of these, I expect a reasonable answer, okay? So everywhere you see white space, fill in an answer, okay? Everywhere you see white space, fill in an answer, okay? And then your data tables, it's obvious where you put your answer to that. And on your graphs, I need something on the graph. So I didn't want to mark all those wrong that turned them in early if you didn't understand you were supposed to answer those questions. So I want to get those back to you whenever you can. Now, if you have questions, when we are in lab today, you'll have time. I'll be glad to go over some of those things. Okay? Yes?
So are you going to drop one of our noise labs?
I will drop you one of those labs for you, yes. But don't start early doing that. You might miss a lab and have to drop that one, okay? Turn in all that you can. Hey, I'll tell you this. What you do on lab, what you did on lab, that first lab, you will see something fairly similar to it, because there was something similar to it in the text. You'll see something similar to it on the test. So don't discount the labs. They should be very close to 25 free points, okay? If you just do it, you get to ask me questions, you get to work as a team, you should be able to get most of those 25 points. Don't waste them, okay? So do something on all of them. Don't turn any blank thing. Write something down, okay? Don't give me blanks, okay? All right. I just happened to think of that when something made it click in my mind. All right, so that was 27, example 2.7, okay? And there's solution 2, you can do it that way too, but this is the most direct way to do it. All right, we did horizontal motion, now we talked about vertical motion. Now we're going to talk about compound motion. As I said before, 3 types of motion. I would go horizontal first. Straight line, horizontal motion. There, unless there's an unbalanced force, you have constant velocity. Vertical motion, you know you have unbalanced force, the force due to gravity. So you're going to have acceleration. If you throw the ball upward, the acceleration is this way. It's going to slow down as it goes. Okay? And at some point it will stop and then start coming back down. And that motion going up and the motion coming down are symmetric to each other. Which leads me to a pretty disgusting example, but it's true. Okay? I don't know if you've seen video and films of these people, most of the time in other countries, I would say almost third world countries, but unfortunately it does happen here too. when people are out celebrating and they fire a weapon into the air. Okay? Guess what? Approximately what is the muzzle velocity, say, of a pistol or a rifle, just a ballpark figure? Do you know?
Depends on the round.
It depends, yeah, it depends on a lot of things. So just a generic number. 900?
1,200.
1,200?
I think at 45 is just under 1,000.
Just under 1,000. So I was saying 900, what units? Feet per second. 900 feet per second is the velocity of that bullet when it leaves the weapon, right? So it goes up, and for every second it's in flight, upward, if you fire it straight up, not a good idea, but if you fire it straight up, then for every second it's going to decrease that speed by, okay, if you said feet per second, you ought to use 32 feet per second. So if it was 900 to begin with, then it'd be 862, or something. So it's going to slow down as it goes up. And it's going to go up quite a few seconds, slowing down just 32 feet per second every second. Okay? But at some point it will stop. Okay? It'll reach zero and then start coming down. And every second that it comes down, it's going to increase 32 feet per second every second. So what's its speed when it gets back here? Same speed it left the weapon. Exactly. So if you did fire it straight up, you better move. Okay? Because it's just like almost.
Wait, what about terminal velocity?
Okay, that's what I was going to say. There is always air resistance.
Right.
So if that was a shotgun, that's going to lose speed pretty good because those are pellets, they're not. But a rifle, a bullet, and why do they call it a rifle? It has rifling in it. What does that do?
It spins the bullet.
Yeah, it makes the bullet spin, which minimizes the air resistance. Okay? So, on its way up at least, it's going minimal air resistance. When it stops and starts coming down, it could be tumbling and stuff, and it could lose a little bit. But I still don't want it hitting you in the head. Okay? Huh? No. So, I thought you said you wouldn't mind. Okay, never mind. Okay. It hitting me in the head. Never mind. Okay. So, my point is, don't move shooting into the air. Because the bullet's got to come down somewhere, and it's going to come down at just about muzzle velocity. Close. Close enough to do a lot of damage. Okay. We had been living in Birmingham just a few months, it seemed like, when it came on the news one night that a truck was heading, I think, east on I-20 somewhere, and the mom and dad were in the front seat, and in the club cab was the baby in a car seat, and they were just driving down the road, and they thought they heard something, but it wasn't very loud. They just thought maybe a car on the interstate backfired or something like that, and they just looked around. The baby was asleep. They thought what had happened, someone was target practicing or shooting something at something somewhere a long way away. No one knows where it came from exactly. That bullet just happened to go up and come back down and go right through that back window and hit the kid in the back of the head. When they did stop, they found out the baby was dead. Wow. Yeah, so every bullet that goes up does come down. Most of the time, fortunately, it doesn't hit somebody, but it could. So, that wacko who was in Las Vegas, he was aiming, and most of those did strike somebody. Not good. Okay. So, let's get to compound motion. So, you either have horizontal motion, vertical motion, or you have a combination of horizontal and vertical. So this would be the guy who shoots like this, up in the air. Not going to hit him, but guess what? There may be someone over there that may get hit. The bullets are going to come back down. Okay? Now, what we call this is projectile motion. That bullet is a projectile. That projectiles out of your weaponry, whether it's cannons or 6-inch projectiles on a ship or mortars or whatever. These are projectiles, an object thrown into the air. Okay, a basketball that you shoot, that's a projectile. Not a very aerodynamic projectile, but it is. A baseball, a tennis ball, a golf ball, all those are projectiles. Anything that goes up into the air, they're going to come down. Here's some basic observations of every one of them. Gravity's acting all the time. All the time. Okay? Have you heard them talk about the quarterback who throws a clothesline pass? Does it go straight to that receiver? No, it doesn't. Gravity is always acting on the ball. Now, it's a very short pass, you don't notice it drop. But if it's any kind of distance, it's going to be going down. He's not throwing a clothesline, he's throwing with an angle. Has to be, otherwise it's going to hit the ground in front of him. And you'll see that happen too when they do try to throw clotheslines. Okay? The acceleration, and here they've introduced it, G. The acceleration due to gravity is given the symbol G. It's independent of the object's motion. If that object's going up, G is going down at 9.8 meters per second squared, 32 feet per second squared. If you throw it at an angle like this, G is going down 9.8. If you throw it downward, G is still going to increase that velocity downward. It's independent of the object's motion. Okay? There's sort of some interesting questions you'll run into sometime. I don't think this book has them. If you were standing on a bridge and you had 3 baseballs, okay? You threw one up at an angle of 45 degrees, threw another one at Chelsea. No, you wouldn't do that. Okay. All right. Chelsea's here. Threw another one straight out horizontally, and threw another one downward at 45 degrees. When those 3 balls hit the ground, what's the velocity of the balls? Which one's faster, which one's slower? Don't worry about that now, we'll get to that later. Okay? You can think about it though. Okay? Compound motion, you do it. So, hint, gravity acts on at all the times, so we will deal with that. Okay. All right. Now, let's look at projectile motion. Let's imagine we threw a ball vertically upward, straight upward. It's slowing down as it's going up because gravity, the acceleration is downward. Velocity is upward, initial velocity is upward. The acceleration is going to decrease that initial velocity at 9.8 meters for every second that thing goes up. Okay? At some point, slowing down as it goes, it's going to stop. Unless you've got quite an arm and you can throw it past the, what do they call it, escape velocity, which nobody can do. Rockets can hardly do that, okay? But anyway, it stops at the top, and then it starts falling and starts accelerating downward at the same rate it was decelerating upward, because gravity is constantly downward. The force of gravity acts downward throughout the flight. Whether you throw it up or throw it down, gravity is increasing the velocity downward or decreasing the velocity upward until it stops it and then increasing it down. Okay, horizontal projectiles. You throw something horizontally. Is it going to remain horizontal? No. Gravity is always going to pull it down. However, the horizontal component of the velocity will not change because the force perpendicular only changes the direction. We saw that earlier, okay? If you neglect air resistance, the horizontal velocity component is always going to be the same. Now, taken with the vertical motion that is pulling it downward, you get a curved path. That's what we're going to do in lab today. We're going to do projectile motion. Curved path. Okay. What in the world is that? Do you want to change the color scheme to improve performance?
Yes.
You're kidding me. X out of that. Okay. I don't even know what improving performance is, okay? Obviously. Okay. Now, the gal here shooting the arrow exactly horizontally. The guy here is holding an arrow at the same height she's firing from. If, at the very instant she releases her bow string, he releases his arrow, which one's going to hit the ground first? Both of them hit at the same time. Way different apart in distance, but at the same time, because the vertical component of gravity is the same throughout the free fall. Okay? Same throughout the motion. Horizontal component, whatever she gives the horizontal component here, it doesn't change. As long as there's no air resistance, we'll assume that. That horizontal component remains the same, but the vertical is going to increase as it goes. So yeah, they'll hit at exactly the same point. Okay? That one will go a lot further. This one only goes down. Not very far at all. Not a very effective arrow, by the way, either. So, did y'all ever see the movie Sniper?
Yes.
Okay. Did you realize how much was involved in shooting? Man, they have to, that bullet's always going to be falling. Y'all did this in Marines, right? Always going to be falling. So you set, I don't know, different people do it different ways. You can set your gauge, I guess you call it, to adjust for the distance you're trying to do. That should take into account when you're those shots of the bombardiers, you know, were you air or infantry or what?
Pretty much
Infantry, okay, on the ground. But you know, if you're over a target, is that when you drop the bomb?
No.
No, you're not going to hit the target. You better. It's all calculated, and we had on even the ammunition ship I was on, 3-inch 50s. I mean, not very powerful weapons, but they were controlled by the fire control computers because it tried to calculate all those kinds of things. You have another couple of things. We won't go into them now, but there's a lot of things you have to account for. Okay. Okay. Passing the football. The only force when you pass a football, you have some control as long as it's in contact with your hand. You're exerting a force on the football. The instant that it leaves your hand, you're no longer exerting any force on that football. From that point on, the only force on the football is gravity pulling it down. So you give it whatever horizontal component it's going to have, not going to get any more. Probably will get less because of air resistance. What do you try to do with a football? Say again?
Curve it.
Yeah,
And
perfect spiral. That's just like the rifling in a gun. You get the spin on it so that it minimizes the air resistance. Doesn't eliminate it, but it minimizes it. There was a passer, I can't remember his name now, for the Washington Redskins. He followed Sonny Jurgensen. You wouldn't remember him either. But he had the ugliest, messiest looking passes. They wobbled and they tumbled and they did all, but he was amazingly accurate. No one figured out how he did it, you know. But he was a very good passer. It didn't look very good, but it was good. So, boy, those punters that can get that ball to spiral when they do, those things go a lot further than those that tumble. Okay. So anyway, but when you're passing the football, once it leaves the hand, the only force action on that is gravity down, except for air resistance. And if you got a nice tight spiral, it's going to try to go. Okay? The vertical velocity decreases as it goes up, increases as it comes down. The guy who catches the ball is going to be just about the same speed that you release it. Okay? The horizontal motion, generally we count it as uniform. There may be some air resistance that would slow it down, but if we're ignoring that, that component doesn't change. Only the vertical component changes. The combination of the two, what is that called? You might call it an arc. The proper name is a parabola. And parabola. P-A-R-A-B-O-L-A.
Yeah.
And you probably deal with them all the time, don't you? Yes, you. Don't your cars have headlamps?
Yeah.
Doesn't it have a mirror behind it?
It does.
You know what that is? The shape of a parabola.
Oh.
Because the light bulb is located what they call the focus of that parabola, and the light turns on and those beams come out close to parallel. Any other shape's not going to happen. Yeah, you deal with that all the time.
I
Yeah.
didn't know that.
And pressure balls. Okay, now right over my head. Okay? Anyone got a satellite dish?
Yeah.
Guess what shape that is? A parabola. Because the receiver is sitting right there in the focus. The beams coming in from the satellite so far away that the beams are coming in parallel. Beams coming in parallel get reflected to the focus from every direction, and that's why the receiver is sitting there on the focus, picking up the combined signal of all that disk and sending it to your receiving or whatever. Okay? Yeah, we use those all the time. That's a parabola. Very useful shape, by the way. Flashlights, same deal. If anything goes out in the beam, that mirror is parabolically shaped. Okay? There we go. So, it goes up, it comes up. Shooting a basketball, except for those of you who dunk it, that's just straight down, okay? But any shot, parabola. Everyone's a parabola. Free throws, parabola, okay? In the NBA, free throws weren't always parabolas. Way back, you could start, as long as you didn't touch the ground, you could leave the circle and do it. Wilt Chamberlain, I think, was just about the only one. Y'all probably don't remember who he is. He was 7 foot plus, way back, and he could leave the thing, not cross the line, and dunk the ball from the free throw line in the air, you know. And so they outlawed that because he was making all his free throws and he was getting fouled a lot too. That's how he scored more than 100 points in a game. Because after they required him to stay behind the line, his free throw shooting was pathetic, you know. He still scored a lot of points. But everything, golf balls, tennis balls, they look like they're beelines, they're not. They're always going downward. Sometimes very little downward. Baseball pitchers, that's a parabola. Once it leaves his hand, that ball starts going down. Okay? That's why the pitcher's mound is a mound. To help account for, he can throw as straight as he can, but they're always going down. Okay? Now, some people swear a knuckleball does all sorts of weird things, and watching batters swing at them, I can believe they may be right. Phil Necro. Never mind. Okay. The only force is downward gravity, horizontal. We've hit all those. All right. That's compound motion. There are several other illustrations in your book. The one of the falling balls, sort of similar to the pool ball that we saw earlier. Multi-flash photography of a falling billiard ball. There it is. Kid sitting in a limb of a tree, a guy, really weird looking guy, throwing a ball up. If he throws it up exactly the same height as the limb, on the way down they're going to be identical motion. Okay? He's throwing on a parabola. Okay. Oops, I have a feeling I jumped out of line somewhere here. So, why do things move? We described motion in the first part of this chapter. So far we've been explaining motion now. Here we really explain motion, and good old Isaac Newton, the 3 laws of motion. He wrote a treatise called Principia. Basically it meant principles of motion is basically what it was. Now, he didn't do these all on his own. As I mentioned before, the year that Newton was born, Galileo died. And it died just a few months before that. So they never interacted, but Newton read Galileo's work. And Galileo had basically outlined just about everything in Newton's first law of motion. Okay? But Newton perfected it a little bit, cleaned it up a little bit, and got the first law. Then he came to the second law and then the third law. He explained all this in this Principia. Revolutionized physics. Okay. At the same time, he developed a whole new math to explain his motion because normal algebra just wouldn't cut it. So he developed a whole new mathematics, calculus. Oh, and at the same time, he discovered the law of gravity. And at the same time, he did light studies that no one else had ever done. Goodness, where was this guy? Where was everybody else beforehand? And he wasn't known to be a particularly modest person, but one time he was asked, and this is one of my favorite quotes of all time, almost surprised Newton said it. They said, Sir Isaac, he was knighted for his work. How in the world did you come up with all this stuff that no one had realized before? How did you see that much further than anybody else had seen? And he thought for a minute, and supposedly, and said, if it appears that I have seen further than others who came before me, it's because I was standing on the shoulders of giants. He attributed a lot to Galileo and others who had come before him. Normally he was not that modest. If anyone questioned anything he did, he attacked with a vengeance. Almost reminds you of some political. No. Okay. So yeah, incredible mind here. The essential idea behind his 3 laws of motion all focus on forces, which we talked about earlier. Here we'll hit them again. Newton's first law of motion, often called the law of inertia. We mentioned inertia before. Anyone remember what law of inertia is? Second? Inertia. Okay, inertia. What is that?
Resistance. It's like resistance.
It's what?
Resistance to movement.
Okay, it's a tendency for an object to resist the change of motion. Exactly. That's a very good description of it. Law of inertia. Okay, I mean, that's what inertia is. So the law of inertia says that every object retains its state of rest or its state of uniform straight line motion unless it's acted on by an unbalanced force. That's it. It tends to not change its state of motion. That's its inertia. Okay? So unless it's acted on by something else, an unbalanced force, it's going to continue either being still if it's already at rest or moving in a constant uniform motion. Okay? Inertia resists any change of motion. Okay? Now, later we're going to hit another concept, and that concept is far closer to what Newton described it as. This is sort of our interpretation of what Newton said the first law of motion was. Okay? Here is sort of a classic example of this. I don't know if any of you have ever ridden a bus or a train that you had to stand in the aisle or something like that. And if that vehicle took off all of a sudden forward, what did you tend to do?
Move back.
Move back. You didn't really move back. You were resisting the motion forward. You tried to stay where you were. It went forward. You tried to stay there. So it felt like you were thrown back, but you really weren't. You're trying to maintain your original state of motion. Or if you're going along at a certain speed, you know, everything's fine, and suddenly it stopped, what did you do? You claimed that you were thrown forward. You weren't. You were trying to maintain your state of motion, which was moving along at that certain speed. This thing stopped and you did. We also do it with curves. When you're riding in a vehicle and someone turns suddenly, we say, you were thrown into the door, right? No, you weren't. You tried to maintain where you're going. The door cut in front of you is really what happened, okay? You tried to go in the same line of motion. That's what inertia is. It's the tendency to resist a change of motion, okay? The bus is originally at rest and then takes off suddenly. You say you're thrown back. No, you're not. You try to stay where you were. The bus just moves out from under you, kind of. I remember one time several years ago, back when I still had my pickup, my lawnmower, probably something around the carburetor, something like that, if a lawnmower has one, was leaking gas. I couldn't mow the yard without it running out of gas. Okay, it was pretty bad leak. So I thought, I got to quit wasting gas. I need to get this fixed. It's something I couldn't handle myself. So I put it on the back of the pickup and tried to block the wheels, chock them, but nowhere down the road, very short distance down the road, every time I came to a stop, there it was against the back. I took off, bang against the tailgate. I tried turning it sideways, make a turn, inertia. It was trying to maintain its state of motion. Okay? You'll see that? I was going to say a can in the back of your truck, but none of you would have cans in the back of your truck. But they're going to roll around, so never mind. We won't go there. Okay. Now, same thing, like I said, when your bus is moving in a straight line, but then suddenly makes a turn, you're not prepared for it. You say you get thrown to the right. And we often call that a centrifugal force. Malarkey. It's not a force. You're just trying to maintain your state of motion. The bus turns in front of you, turns and hits you in the side. It feels like you're thrown outward. No, the bus is actually come in. The force is needed to overcome the inertia and change the direction. Which is, by the way, what we've mentioned before, why Talladega or highways and things like this are banked. Because you've got to have something to force you to change your motion. If that was flat, and I can remember some of the old roads in the country, they always did a road in a crown, so water would run off both ways. And if they did the crown around the curve, it kept the crown there. If you were in that outside lane, it was throwing you outward. Where, that's not a good thing. Those are usually called death corners or something like that. They're not the way to build a road. All right. So that's the first law of motion. Let's go back and say it again. Every object retains its state of rest or state of motion, uniform straight line motion, unless acted on by unbalanced force. First law, law of inertia. The second law is pretty similar to it. But this one says this is unless acted on by an unbalanced force. The second law says, well, what if there is an unbalanced force? And they call it a net force. Forces cause accelerations. That's the key. Forces cause accelerations. And what's an acceleration, by the way?
Change of speed.
A change of velocity. You got it. Change of velocity for change of time. Time rate of change of velocity. So, if a force causes an acceleration, I'm going to write down the formula. They should have already done it for you. They gave you units. Here is, here it is. Here is that formula. The net force, that's the unbalanced force. When you take out all the balanced forces, whatever net force you have left over, that produces, here's what you would say. A force is proportional to the acceleration is proportional to the force. What's the constant proportionality? The mass of the object. Okay? The mass is related to the inertia of the object. So you see these are pretty closely related. If there is an unbalanced force, a net force acting on it, that's going to cause an acceleration. And what's an acceleration? A change of velocity. So let's take that. What is our basic unit for mass in the SI system? Kilogram, you got it. How about acceleration? Talking only about units here.
Speed.
No, speed is different from acceleration. What's the units for acceleration? Get to know these. You did it in the lab. Some of you are very good about putting the units in. Some of you are miserably poor about putting your units in. Please put in units, okay? What's the unit for acceleration? Anyone remember? Meters per second. That would be a speed. Squared. Meters per second squared. So a kilogram meter per second squared, that is, unit-wise, that is a Newton. Now, where do we get the name Newton? Sir Isaac, of course. And guess what? That's why the unit is capitalized. Kilogram's not named after anybody. Meter's not named after anyone. Second's not named after anyone. Newton's named after someone, capital letter. Newton. Kilogram meter per second squared. Units are your friends, okay? These are the fundamental units. That's the derived unit. Okay, forces are in newtons. How about English or U.S. customary system? What do we measure force in with that? Say again? No, that's speed.
Yeah.
Force. Same unit. Stand on the scale.
Weight.
Unit. Pounds. Yes, that's the unit in the U.S. customary system. Pounds. Now remember, I think I told you, we don't use mass units in the U.S. customary. We just use weight units, which are not mass. But what is the unit? No one ever uses it. I think I gave it to you early on. Yeah, like a little slimy slug. Yeah, it's a slug. We don't use it, and that would be a slug foot per second squared. That's approximately what a pound is. But no one uses slugs, so don't worry about that. Okay? So, forces are proportional to accelerations. What's the unit of proportionality? Constant proportionality? The mass. Okay? Now, fairly important concept here. A lot of times we'll talk about forces as if they're just a measurement. But remember, velocity is what kind of quantity?
Speed.
Okay, speed is a scalar quantity that just measures the number, what your speedometer does. Velocity also measures, we talked about this before, direction as well. What? Say again? What would that be called? What kind of unit measures not just magnitude but also direction? The velocity measures it. What kind of unit is that? That includes direction. A vector. Okay, scalars are just magnitudes. Vectors are magnitudes with directions. Okay? So if velocity is a vector, v, vector, velocity, vector, okay? Acceleration is also a vector. So therefore, force would be a vector. How about mass? Scalar. No direction associated with a mass. Okay? But pounds measure forces, they're directed. When I stand on the scale, the gravity is pulling me downward with that many pounds. Depends on my mass, but that many pounds. So forces are vector quantities, accelerations are vector quantities, masses are scalar quantities. So that's the constant proportionality that relates acceleration to forces. The more force, the more acceleration. Okay? That would mean if you, we'll use that later. The more mass, though, the lesser acceleration, because you see, if you divided both sides by mass, then mass would be in the denominator, so the greater the mass, the less the acceleration for a constant force. Or the other way, the greater the acceleration for a constant force would it be on the smaller mass. So those are inversely proportional because they're multiplied on the same side together, but when they're directly proportional, they're on the opposite side in the same position. Okay. All right. I think I know what slide was supposed to be here. Maybe it'll show up later. Let's see. Yeah, it'll show up later. They put it in a different place. So, this is referring to a picture. Here's the picture. Here's a guy on his bike, tooling along here. He's applying a force, okay? His turning of the wheels here is hitting the rubber on the road here, and the friction of the rubber on the road is in this direction, so the force, applied force, is in that direction. Okay? Friction always opposes the force. Okay? Without friction, he doesn't move. Like hits an oil slick, spins without friction, he's not moving forward. It's always falling down. Okay? Now, there's also air resistance that he's bumping into air resistance. That's slowing him down. So he's having to apply enough force to overcome the road friction and the air friction. Okay? And if these two add to be the same, what's his net force? These two add to be the same length as that, what's his net force? Zero, because adding vectors, you have to account the direction. What would that tell you? If he has zero net force, what else is zero? No. Acceleration, because force is proportional to acceleration. So if the net force is zero, then the acceleration is zero. Which means what about his velocity? It could be. All it requires to be, though, is constant. Constant velocity is zero acceleration. If you're on cruise control, you're not accelerating, right? Are you at a rest? Are you stopped? No. You're going 60 miles an hour, 70 miles an hour, but you're not accelerating. Acceleration is a change of velocity per unit time. So if the applied force is balanced exactly by the resisted forces, then there's no net force. The acceleration is zero. That doesn't mean he's at rest. It means he's at constant velocity. He could be at rest. Then it would be zero acceleration as well, as long as he's not taking from rest. So, that would be the situation there. No acceleration, constant velocity. I think we beat that to death. Now, what if, oh yeah, they don't have it on here. All right. In the text, you'll see another picture of a bicycle, but this is a tandem bike. A bicycle built for two. Okay? So what if, now this is a tandem bike, he's pedaling along here, and he's the only one on the bike, then that's fine. But what if his girlfriend or his wife gets on the back seat, and he can't see, she's just sitting there? Is he accelerating as much for the same force? No. Double the mass, half the acceleration. Okay? If you have a net force. Okay. That was the picture I think was supposed to be on the other. Okay. Now, a little bit of a timeout here, okay? And let's look at the concepts of weight and mass. I've already mentioned these to you before, okay? Now, a net force is related to an acceleration. If there's a net force, you're going to be accelerating. Okay. The formula is this. Net force, and you should say net here, net force is mass times acceleration. Remember my example of that airplane flying at 500 miles per hour at straight level flight? What's the net force on it? Zero, because it's going at a constant speed, not turning direction. So the net force is zero. Okay? But if it was accelerating, there would have been a net force on it. There's lots of forces on it, including the force due to gravity, which we call weight. Okay? Now the forms look very similar. Generally, weight is not a net force. It may be. If that's the only thing acting on an object, that may be a net force, and then its acceleration is the acceleration due to gravity. But when I'm sitting here in the chair, I have weight, and that's my mass, big as it is, times the acceleration of gravity. That's not a net force, that is a weight. That is my weight. Notice the forms are very similar. This could be a component force. Like if someone started pushing me in the chair here, my weight would be pushing down, the floor pushing up. He's pushing this way, the air resistance or whatever is pushing that way. This would just be one of the component forces, my weight, but that's your mass times your acceleration due to gravity. This acceleration up here is your change of velocity. That may be less or greater, it doesn't matter. It may be minuscule. It may be zero. Acceleration due to gravity is always 9.8 meters per second squared, anywhere on the surface of the Earth, or 32 feet per second squared. Okay, acceleration only in free fall is that acceleration equal to g. So I sort of hate they did those. This is true only in free fall. The A is equal to g, is equal to that. That formula up top is net force. That's acceleration is change of velocity. The weight is mass times acceleration due to gravity, whether you're moving or not. That's a component force. Okay? So mass is a quantitative measure of inertia. The amount of matter you have. Okay? Think of, I think I gave this example before. I'm going to there you are. Okay. Oops. Yeah. I'm going to throw a ping pong ball as hard as I can at Daisy back there. Okay? You better duck, right? No, he's not going to bring it all. Okay? As hard as I can throw it. He's still not going to worry. I'm going to throw a bowling ball as hard as I can toward Daisy. Everybody else in between is going to be ducking too, in case it doesn't quite get there. The ping pong ball, they don't care. Why? Because the quantitative measure of inertia is the mass. And the mass of a bowling ball is way bigger than the mass of a ping pong ball. So that's inertia is related to mass. Weight is the force of gravity acting on any mass. Okay? Pounds and newtons measure force. So when we relate pounds and kilograms, we're talking apples and oranges there. Sure, on the surface of the Earth, they differ only by a constant. Okay? The proportionality constant. But they still, pounds is a vector quantity, newtons is a vector quantity because they measure forces. Kilogram is a scalar quantity, it's a measure of mass alone. How much of the object is there? Okay? On the surface of the Earth. You get off the surface of the Earth, like in outer space, the Moon, Venus, Jupiter, wherever you are, then your weight can change like crazy, but your mass is still the same. Because that is a vector force, mass times acceleration due to gravity. On the surface of the Earth, acceleration of gravity is constant. Once you get far enough off the Earth, then it starts dropping off. Okay. So don't relate those two as if they're the same. Even though the scales at the grocery store will have pounds on one side and kilograms on the other. And you'll see in math books, 1 kilogram is 2.2 pounds. No, it isn't. It's equivalent to it, but they're not the same. One's measuring force and one's measuring weight, a mass. Okay? So don't relate them the same. Newtons and pounds, yeah, those are related. They're both forces. All right. Oh, wait. Before we go there, I need some white space. Here, we got it. Example 2.8. A 60-kilogram bicycle. What is that a measure of? Mass. Okay, that's a mass. 60-kilogram bicycle and rider, that's the bicycle and rider together. You don't want to be riding a 60-kilogram bike. 120-pound bike, nope, 132-pound bike, no. You don't want that. That's you and the bike. That's bike and rider. Okay. Accelerate, there they gave it to you, at 0.5 meter per second squared. Is that a good unit for acceleration? Yeah, you better believe it. How much extra force had to be applied to make that acceleration happen? Anyone remember the formula? Basic formula for Newton's second law.
Mass times acceleration.
Yeah, force, net force is equal to mass times acceleration. So it's just a simple plug and chug. That's 60 kilogram mass times a 0.5 meters per second squared acceleration. And what would that give you? 30 what? You could either write it as 30 kilogram meter per second squared, that's the fundamental units, or 30 newtons. Very good. 30 newtons. Okay. The SI unit for force is newton. Okay. All right. That was 2.8. Let's go to 2.9. Bottom of the column, right-hand column on page 43. Okay? What is the acceleration? This time acceleration is what we're looking for. Of a 20 kilogram cart. What is 20 kilogram a measure of?
Weight.
Mass, okay. If the net force on it is 40 newtons. So net force is 40 newtons. Say again? What formula? Net force equal mass times acceleration. Now you can either chug and plug or plug and chug. You could either solve this for acceleration first and then plug in the numbers, or plug in the numbers and then solve for acceleration. I don't care which way you want to do it. Plug and chug. So plug them in. We know the net force, 40, and it says newtons there, but I want to put the fundamental units. What is a newton? A kilogram meter per second squared is equal to the mass, 20 kilograms, times acceleration. So what do we do to solve for acceleration? Second? And how do we do that? Oh, is that added? Divide. That's multiplied. 20 kilograms meaning 20 times kilogram. You only undo addition with subtraction, you undo multiplication with division. So we divide by 20 kilograms. So you divide over here by 20 kilograms. And 40 divided by 20 is, of course, 2. But don't forget your units. Divide out the kilograms here. And what are we left with? You divide everything here. 2 meter per second squared. All right. And probably that should be, well, I don't know. You could put 2.0. I'm not going to argue either way. The book is not very consistent with that. The first one I forgot to check it, but it was 30 newtons. And this one just says 2 meters per second squared. Very good. All right.
Mr. Fowler,
Yes.
can we use to find out, like, okay, you got to multiply, divide, use that formula. Can we use the Ohm's law there?
Yeah, you could do that too. Very good point. If you know that F net force equal MA, then put the thing that's equal on top, net force. Do you like circles or triangles, or does it matter? Circles. I like circles too, okay? I like triangles too, okay? That's a division line, that's a multiplication line, okay? The vertical line is multiplication. Put mass down here, acceleration there. Because the two things that are multiplied go down here, the thing that's equal to is up here. But since you're looking for acceleration in this problem, you're looking for acceleration, force divided by mass. Exactly. Is that what you meant? Yeah, exactly. But do your units too to make sure that it makes mistakes. Okay? Pretty exciting stuff, huh? Okay. Now, then we did weight and mass. So we have a couple of examples there too. So let's hit those before we go to Newton's third law. Example 210. What is the weight? So we're here looking for weight. That's your unknown here. What is the weight of a 60.0 kilogram person? What is that a measure of?
Mass.
That's a mass. Okay? On the surface of the earth. What does that tell you? What formula relates weight and mass? Weight and mass. It looks a lot like Newton's second law, but it's talking about different things. Weight is the same as force. And say again? It's not MA. What acceleration we're talking about with G? Gravity, the acceleration due to gravity. Okay, we know we're looking for weight. We know the mass. Do we know G? No. We got to find out weight. We need to know G. Does anyone know G on the surface of the earth? 9.8. You're absolutely right. So your assumption here, as soon as you saw on the surface of the earth, you can say G is equal to 9.8. What units? No, meters per second squared. Yeah. And acceleration, meter per second squared. So plug it in. Mass is 60.0 kilograms times, when they're written next to each other, that's multiplied, 9.8 meters per second squared. And that gives you 6 times 8 is 48. Carry of 4, 54, 58.8 kilogram meter per second squared. Or, what is a kilogram meter per second squared? Newton. Now, here's the deal, folks. Even though this had 3 significant digits, that only has 2. If they had given you 9.81, which some physics book do, then you could use that, and then that would be a little bit different number. Then you could justify 3 digits. Since you don't have a 2 here, what do you need to do here? Round it to, and what would that be? 59 newtons, or kilogram meter per second squared. And let's see if the book did it. No. I botched up. I forgot that 0 in there. It's 588 kilogram meter per second squared, which rounds to 590. Sorry about that. I was multiplying 6. I forgot to multiply my 0. 588 kilogram meter per second squared, or rounding that 590 kilogram meter per second squared, because you only have 2 digits. That 0 is not significant. If you left that in there, that would indicate 3 significant digits. You don't have that. So that is 590 newtons. Okay. And you should have caught me on that, because this is close to 10. 10 times 60 is close to 600, not close to 60. Answers need to make sense. Okay? Let's do 2.11. Let's see if I can get that one right. Okay? A 60 kilogram person, again, what's that a measure of? Mass. Okay, that's the mass of the person. Okay? Weighs 100 newtons. What's that a measure of? That's your weight. But he weighs this on the moon. What is the acceleration of gravity on the moon? How would you get that? Okay, what's your formula? What do we just use? M equal? W equal? mg. But this is acceleration on the moon, not acceleration on the earth. So you want to plug and chug or chug and plug? I don't care. You want to plug in first, or you want to solve for G first? Plug in first. The weight was, you were told, he weighs 100.0 newtons. Only when I'm solving problems like this, I like to put the fundamental units. What is a newton? Fundamental unit for newton. Kilogram. Kilogram what?
Per second squared.
That's close, but not quite. Meter per second squared. Mass times acceleration. Acceleration is meters per second squared. Okay, so that's it. Is equal to mass. That was 60 kilograms, 60.0 kilograms. And then times G for the moon, which is what we're looking for. This is the unknown. Oh, I forgot to write that down. G for the moon, that's the unknown. Okay? So let's solve for it. What would we do? Divide. Divide both sides by 60.0 kilograms. Divide both sides by 60.0 kilograms. Okay, kilograms go out, 60 kilograms go out here, so you have G on the moon is approximately equal to 100 divided by 60. Well, I'm going to make that a little easier. Let's make that 10 divided by 6, okay? Divide numerator and denominator by 10, that's fine. 10 divided by 6, which you could say is 5 divided by 3, which is 1 2/3, which is 1.67. What units? Meter per second squared. So you see you don't need those little black boxes of calculators. Okay? 1.67 meters per second squared. Which, by the way, is about approximately 1/6 that on Earth. Okay? So if you multiply that by 6, you would get 10, and on Earth it's not 1/8. So yeah. The acceleration on the moon is about 1/6 that. So, if you want a weight loss program, go to the moon. you'll automatically weigh 1/6 what you do on Earth. I just lost 100 and some odd pounds. Okay? Just like that. My mass is still the same, but if you're interested in weight loss, that's one way to do it. Sort of expensive weight loss plan. And the sad news is when you come back to Earth, you weigh exactly. You haven't lost it. You gained it right back. All right. Enough of that foolishness. All right. We are right at the point to do Newton's third law of motion, but we don't have time to do it. That's where we'll start next time. Okay. Right there. Okay. So, let's shut down shop here. Well, let's pause shop here anyway. I hear people banging things around. Please don't. All right. You need to read the first 2 pages of the lab, page 65, 66. Have several formulas there. Our procedure starts on page 67. Now, I've modified the procedure a little bit to make it go more quickly, okay? Because I would like y'all to be able to get home a little bit earlier, okay? So, do not adjust the ramp. Here we are, okay? Did you get a lab? No. You got one now. Okay. All right. Do not adjust the ramps at all, even though your paper says to. I have adjusted the ramp. You don't need to change it. It says adjust the ramp so that A, I'll get back here so it gets up. A is someplace on the ramp, okay? And it says the upper, and this is the part where you're not going to do. The uppermost part of the ramp is 10 centimeters above the surface of the tabletop. Here's what I want you to do. Now, first I want you to notice how far is the end of the ramp from the edge here. That's not a yardstick. A meter. Okay? Now we're going to be measuring, though, not in meters, but in centimeters. Okay? So how many centimeters is that? 100 centimeters. So that's why I have this laid off here. That's how I wanted it not messed with. So that's 100 centimeters. So here's what you're going to do. Rather than adjusting the ramp, take your meter stick and fix it so that it is 10 centimeters. You have a lamp? Yes. Okay. This group already has 7. How many groups do I have? 2, 4, 6, 7. You're in that group. 2, 4, 6, 7. All right. That all works out. Okay. Yeah, here's Chris. We're going to say, what is Chris? Okay. So what you're going to do is measure 10 centimeters from the bench top, and that's where you'll be releasing the ball from for your 10 centimeters. Rather than adjusting this, and that messes up this, let's just keep all that in place, and wherever you find the 10 centimeters, that's where you release the ball from. Okay? Second? That's procedure right here on page 67. Okay, procedure 1. Do not adjust the ramp, but measure from the desktop to the ramp 10 centimeters above the surface of the tabletop. Okay? That's where you release the ball. Now, we've already measured the horizontal track. What's that? 100 centimeters. Very good. You'll release the ball from the 10 centimeter mark. Okay? The person with the clock here doesn't have to be the one releasing. But what you'll do, you'll start the clock when the ball, here I'll do one. This is not 10 centimeters, but you'll start the ball when it's there and there. Okay? Start, stop. Start when it hits the desktop. Stop when it rolls off the edge. Okay? Now that one is immaterial. That happened to be 0.87 seconds. Now I saw some of you on your first on the last lab, we're trying to give me milliseconds and stuff. That's not 87 milliseconds. That would be 870 milliseconds. So don't transfer it, just put 0.87 or whatever it happened to be. That was not from 10 centimeters, so that's not going to be right. And again, reset. Okay? Does everybody understand that?
Yeah.
Did it make sense?
Yeah.
Okay. Now, whoops, I got your clock too. Okay. Now, release the ball, time how long it takes just to move the horizontal. Not how long it is on the ramp. That's what we did last time. We're not doing that now. We're just doing the time of the horizontal portion there. When it touches the tabletop, it starts. When it falls off the edge, that stops. Okay? Now, you can go on and take your 3 time measurements if you want to do that, but record on your data sheet. Turn back to, now be sure you do this on page 70. Projectile motion from a ramp, the ramp 10 centimeters above the tabletop. That's where you're starting. That's on page 70. So you put your 3 times down there. Do 3 measurements 3 times. Okay? Now, if one of those times is way off, like the stopwatch didn't work right or something like that, repeat that. Okay? You're not doing 10, are you?
No, I was just.
Okay, I was just going to say, that was way more than 10. Okay. All right. So, you do your 3 times. Then you can stop and calculate your velocity. How do you get your velocity? Say again?
You gotta use a formula.
And what formula is that? There aren't many of them, are there? Yeah, there are a lot.
Isn't it like distance and time?
Distance divided by time. That's your speed. Okay? What's your distance?
10 centimeters.
No.
100 centimeters.
100 centimeters divided by whatever time you measure. Okay? Now this time we're not throwing out high and low like we did last time. This time we're calculating the velocity for each one, and then on the next line down there on page 70, average velocity. How do you get the average velocity?
Add them together, divide by 3.
Add them together, divide by 3. Very good. Okay? And then at some point you will come here, take your meter, oh sorry, I didn't know that was on there. And you measure what your vertical drop is. Okay? And get it to the nearest tenth of a centimeter. Okay? Be sure zero's on the floor, the 100's on top. Otherwise you're going to get a weird seeming
So
number.
is the vertical distance going to be the same for all of them?
For all of them, yeah. Because you're not going to raise this up there. Okay. Good deal. All right, so if you want to, you can start there. Okay? Where you're going to get stuck is on delta X. Okay? Let's go back to your procedure. So you're going to record your data in data table 6.1, make 3 runs, find the average velocity. Measure and record, that's number 1 on page 67. Number 2, measure and record delta Y. I just showed you where to do that. Now, here's the part that's going to take some effort. Can everybody see this? Okay? Notice number 2 on page 67. It says solve this equation, and that equation is delta Y is equal to 1/2 G times delta X squared divided by V sub X squared. Okay. It says solve that for delta X. So how do you solve that for delta X? This is what you're wanting to solve for, delta X. First thing you would do.
You cross out the X.
Second?
You cross out the X squared.
Okay, this is a delta X squared here, this is V sub X here. Those are not the same units. Okay?
Plug in what you got.
No, don't, yeah. Let's do what they say. Solve for delta X. Well, first thing, here's the denominator here. Let's multiply both sides by 2. Right? That will wipe out that denominator. So now you have 2 delta y is equal to g times delta x squared over v sub x squared. Well, here's another denominator, v sub x squared. So let's multiply both sides by v sub x squared. So multiply this by v sub x squared. Okay? That wipes these out. Okay? Two more things to do. First thing is, divide by g. Divide by g. That wipes out the g. Okay, now I'm going to rewrite this. It won't look quite the same, but it is. Delta x squared is equal to, I'm going to start with the 2, delta y, v sub x squared divided by g. That's what we did. My writing's sort of lousy.
So that's now.
No, that's delta x squared. We want to solve for delta x. How do we get that?
Can't start the square.
Huh? How do you undo a square?
Square root.
Take a square root. So to get a square root, you do the square root of this thing. Okay? Now, okay? Let's take a look at what we got. Here's the formula we'll be using. 2 times delta y, that's the height that you had there. V sub x, that was what you just calculated when you average your velocity. That's your horizontal velocity. V sub x. Square that, and then divide by g. What's g?
How much the ball weighs?
No. We used it several times. It's the what of gravity?
Point of gravity, 9.8
9.8 what?
meters per second.
Square. Meters per second squared. It's an acceleration, not a velocity, an acceleration. And you are correct that g is 9.8 meters per second squared. But what the problem is, what are we measuring our lengths in? Centimeters. So we don't want to use meters per second squared. How many centimeters per second squared is that then? Anybody know?
980.
980. So the g you'll use is not 9.8 meters per second squared. You'll use 980 centimeters per second squared. That's it exactly. All right. So that's what you'll use to calculate your delta x. Okay? You ready to get going?
So what is that? That's 2 delta y.
Okay, what's this again? I hear something, but I can't make it out.
He's talking to himself.
Oh, I see. As my dad used to say, that must be an intelligent conversation. Okay, never mind. Okay. Okay. Any questions? Okay. If you have questions, ask, or you can get going, and then if you run into questions, ask.
I need to come look at this sign here.
You need to what?
I need to come look at this sign.
Okay.
I ain't touched it, man.
Okay.
Very careful. There's a gap right there. You can close it.
Okay. It doesn't matter that much, but I try not to have it there. So I might need to.
Yeah, no, look at me. Because I don't know what's going on. I ain't even lying. I ain't even missing nothing.
That feels about right to me, isn't it? You got out of that? Yeah. Okay. The important thing, that really wouldn't matter too much. The important thing is that you're able to get 10 somewhere here, 20 somewhere there, and what's the first 30? Somewhere about that, but you get the general idea. Okay. Good. Okay.
Going.
Y'all can start your start your tens.
Hey, that was his last.
Okay.
His last. Hey, Cook.
Okay, there may be a question here. Wait a second.
He took his last.
Oh, why? You don't need one, do you?
Yeah, I need a
I got it up here. Sorry.
Yeah. You want to let y'all do it? Go ahead. Okay.
Went from here to this.
No. That's just the G here.
The G
That's
is
just
G equals.
no. Yeah, G is 980 centimeters.
Just have the
Centimeters per second squared.
That equals half gram over.
Yeah. All this was to get, here's what your final formula is. Delta X is equal to the square root of 2 delta Y V sub X squared divided by G. All that take us to the root. And G is this, 980 centimeters. This is in meters per second squared. This is in centimeters, that's in centimeters, everything's in centimeters, and in centimeters per second.
If you would have just wrote it down.
It's the same value, it's just a different number.
Delta X equals 2
It's not written down.
delta Y V sub X squared.
Yes.
Okay.
It might help if I just spread everything out.
Okay.
Now, remember, this is the denominator just like the 1/2. I like to write them below rather than slanted because you don't always see that. First thing I want to do, I want to solve for this one, delta X. So I want to get the 2 over there, so multiply both sides by 2. And then the 2's go right? Okay. So then let's multiply both sides by delta, or V sub X squared. And multiply that.
This side right here?
No, the other side of the equal sign, yeah. Okay? And these crosses, divide by. Okay? Then let's divide by G. Divide that side by G.
Somebody got time?
The whole thing, yeah. Yeah. Okay? And these pieces go out. And that leaves you just delta X squared. So let's write it down. Delta X squared
We have to do 3 or no?
is equal to, okay. Let's start with the 2.
You ready?
2 delta Y times V sub X squared divided by G.
That's going to be
And then the square root of the whole thing. The whole thing. Yeah, square root, yeah. Right? Square root. And that counts to G, so make sure it's down there. Yeah. No, the square root. Yeah. Just make sure it goes down the root. Yeah. That's good. And that undoes the square, so you can wipe out the square. That's your delta X. Delta X is that thing right there. Okay?
okay. So then after that, you just plug and charge.
You just plug and charge. Okay, were there any questions so far?
103, 109.
I guess you realize you have to have your path cleared here. You don't want it hitting any rulers or.
Find the velocity of the 3 and value of the velocity, correct?
Yes. So you calculate the velocity for each one. This is 100 centimeters divided by every other. Now, whatever time you play off, redo the one you play off. I heard someone say, do we have to do 3? Yes, that's what the lab calls it.
0.96 is the first. Somebody just write down the times. 0.96 is the first.
If you have any questions, please ask, folks. And since I don't hear any questions now, I'm going to pause this. Remind me to, yeah, well, I'll give you some hints on it. Okay. All right, when you're ready to start doing the graphing, okay, there is on page 68 results. Make a graph with velocity on the horizontal axis and distance on the vertical axis. Okay? Use the v sub x that you calculated when you average, that's your v sub x, that's your velocity, and your delta x, that's the one you calculated from that big formula I just erased, that's your delta x. Okay? It says calculate the slope, including units. Now I put at each station several rulers, so share those among yourselves. I don't have enough for everybody, but each group should have some. Okay, and here's a hint. Okay? Here's the graph. Look at the last page. It's not numbered. There's your graph. Now, someone give me approximately what your three velocities are.
182.
Okay, that's one.
143.
Okay.
106.1.
Okay, so going from about 100 to close to 200, right? And that was to be on the horizontal scale. What was your delta x's?
Yeah, delta x.
Yeah.
80 centimeters, 63, and 47.
Okay, from about 45 to 80 or 90. Okay? So, since you want your, if you'll pay attention here, since you want your v sub x's on the horizontal, is that right?
Yes.
That's what it says, right?
Wait, these
Mm-hmm.
Yeah, you're right.
Yeah. The velocity's on the horizontal. And since the velocities are carrying a larger span, then put those on the long side, and your delta x is this. So turn your graph landscape, okay? And give me the high and low of your velocities again. 100 to 200 approximately?
Yeah.
So if you did 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, will it all fit within 190?
Yeah.
Okay. That would be, so put your 100 at this end, 110, 120, 130, 140, 150, 160, 170, 180, 190. Will that cover everybody's velocities?
Yeah.
Okay. And then what were your ranges of the delta
50
x's?
to 80.
40 to 80 approximately?
50 to 80.
50. So 50, 60, 70, 80. Oh, you can do bigger than that, okay? So 50, 60, 70, or 50, 60, 70, 80. So 30, 40, 50, 60, 70, 80, 100, 110. That'll cover everybody, right?
Yeah.
Okay. So, for your 10, you go, it was something like 100 and something another, and then go up to whatever the velocity was. Get your scales first, and then put your points. X, Y. I mean, your velocity, delta X. Velocity, delta X. Velocity, delta X.
So just
When you get,
line up to the, what you say?
okay.
Yeah.
Where'd you stop and start on the?
Okay.
Uh,
What were your numbers? For,
We had 106,
no, okay, for your these. 45?
45,
Or, yeah.
56, and 79.
Okay, so let's say 40 to 80.
40.
Okay, so if you did 40, 50, 60, 70, 80, let's see, 30, 40, 50, 60, 70, 80, 90.
20.
Yeah, that would be 20, 30, 40, 50, 60, 70, 80, 90. Yeah, I would say 30, 40, 50, 60, something like that. Just get it sort of in the middle. Okay? Then you have three ordered pairs, one at 10, one at 20, and one at 30. And plot those ordered pairs, and then draw your line. Hopefully it'll be pretty close to a straight line. Then you calculate your slope. How do you do slope?
We're not here. We don't have to turn it into
Rise over run. Exactly. Okay. Did you have a question you were saying?
I've got it.
Oh, okay.
Yeah. I'm going to help him. They weren't listening to what you were just saying, so I'm going to explain it to them.
Okay. Any questions? Any questions?
You said to the graph, that's supposed to make a straight line.
What's that?
Never mind, I got it.
Yeah, it's pretty simple.
Okay, do I need this board anymore?
No, sir. No.
Okay, y'all aren't bored? Good. Okay.
We're going back to class, right?
Wait a second, what?
We're going back to class? Yeah. All right, back to class.
I want to hear turn it in. Because this ain't that really the answer. But all of them, some of them just instructions, not all of them questions. Like a lot of them like place a cup on the floor. And use your stuff. Like not all of them. Like you see my calculations, our calculations gonna be
Hey,
accurate.
Doctor.
Yeah.
On the one we done yesterday,
Right.
I didn't go down to there for every one of the little things. I just put at the top, I put what the units was.
Right.
I didn't go down there and put all of them and fill it up.
Okay.
Yeah, I put them at the very top
Right.
one.
If you got that, I like to see it somewhere. A bunch of people didn't put it anything.
Yeah.
They just put numbers.
Everybody's
Numbers
gonna
don't
get
get
out of
it
here.
without units, yeah.
There's an extra one we had.
Okay, that may have been mine. All right, thank you.
My charger got caught. I think it's like the charger got caught in my phone. The door is locking the door. Alright, so I'm gonna take this picture. I can't even watch it.
Okay. Anyone think there may be more questions? Okay. All right.